Alright, so we're going to begin by discussing our analysis or assessment on the paper Computational Models in 3D Printing Materials and Structures, which is going to be connected to the content of the Continuum Mechanics course. We will share our testing and results and demonstrate the paper's effectiveness based on our evaluation. As a general overview, we'll start with discussing the methodology of the paper and share our results of the experiment that we ran and discuss this testing process and what that looked like. Some connections to the course will later be shared, and finally we'll finish with a debrief and a few critiques on the paper. So within the paper, a void shape is discussed, and it is explained to be classified by a closed form differential mapping function. And this function is essentially used along with the void fraction to modify the moduli of the material in a continuous orthotropic model. This shape of the mapping function is chosen to fit the mesostructure of a particular print, and you'll see later on in this presentation where we have selected a void shape for our particular 3D printed material. And this interaction of the function is essentially acting as a model of the recrystallization and bonding between layers after a melt flow, and summarizes the effects of the dynamic processes of a plastic extrusion. And below you'll see a few different pictures which are demonstrating the physical representation of these void shapes and what those look like, which we will later compare with our results of our 3D printed material.
The void shape factor and the void density are then used to calculate different elastic properties in the fiber direction or perpendicular to the fiber direction. These are then used to form the components of the layers C tensor, or the elastic tensor. It's worth noting that each layer will have its own local coordinate system, with direction 1 being in the direction of the fiber, which will all be uniaxial in this analysis, and direction 2 being perpendicular to the fiber in plane of that layer, making direction 3 the direction in which the layers will stack. We can transform between each coordinate system per layer using a transformation tensor, which just takes the input of the angle difference between direction 1 of each layer. We can also use this tensor with a different angle input to calculate or find our global coordinate system. The global coordinate system will be used for the overall layup, or the total part consisting of all of the layers. Finally, we're able to use the plane stress assumption and collapse our 6x6 elastic matrix for each layer, or elastic tensor for each layer, into a 3x3, which is called the Q tensor. We then go layer by layer and add up Q in the global coordinate system for each layer. We perform 3 integrations with varying powers of layer height and form the A, B, and D tensors. The A tensor is a stretch stiffness tensor, the B tensor is the bond stiffness tensor, and the D tensor is the flexural stiffness tensor. These are then used to form a global response tensor, or a global C. Then we can input a global strain state and output a global stress state. Representative volume elements are then created at each filament interface. Strain energy is calculated using the local stress and strain at each location transformed into global coordinates. We do this by multiplying 1/2 times stress times strain. Finite element analysis was done using this model to construct different complicated shapes of which the mechanical performance was of interest. This is computationally expensive, however, so if valid, the closed form solution of classic laminate plate theory is useful for rapid global response approximations.
So to the right is an example of our calculations for the overall elastic moduli of the 3D printed part. And this was pulled directly from the paper and their examples of how you would calculate this overall elastic moduli. And these results will be used during the testing process to verify if they are true.
So now that we have our effective moduli from that MathCAD sheet, we're going to take them and input them into a MATLAB code. The other inputs for this code will be the tensile strength, which is from Polymaker, the manufacturer of the filament, and can be found in their TDS. We'll also input the stack up of layer rasterization angles, so the angles that the 3D printed layers will be printed at, how many layers we're going to print, the thickness of the layers, and the width of our test section. Then the code will build a C stress tensor for the overall body and begin adding load to it. For each increment, the Psi-Hill failure criterion will be used to check and see if each layer has failed. Any layers that have failed will be denatured by removing them from the stiffness matrix and stiffness matrix recalculated. And once all layers have failed, the code will report out the final load value and graph the function. The Psi-Hill failure criterion that we're using is common in composites and is based essentially on stress energy and incompatibility, and will be discussed more in the connections to class materials sections. Using the samples we're printing, the code outputted a overall breaking load for our samples of 501.4 newtons, which is our result for this section that we will then be testing in the extensions. Step in our physical testing was to print an orthotropic sample, which basically means all the lines across all layers were oriented, take a cross section of it without distorting it, and then analyze the void shape in an orthotropic example of our PLA 3D printed material. You can see on the right, we took microscopic imaging, brought it into GIMP, and measured our void shape and void fraction, which were then input into the codes previously discussed. For our particular process, we got a void fraction of 7.57%, and we chose the mapping constant of 0.25 from the mapping functions because it easily encapsulates the curved surfaces that are slightly concave and the curved corners of our voids. Our voids are triangular. However, this approach is still valid because the mapping function is just used to estimate the stress concentrations and the boundary properties. So it's more important that we have those smoothly curved boundaries represented than the actual exact square versus triangular shape. Whereas the void fraction encapsulates the strength of that overall system. So once we knew the properties of our materials, we could start printing samples to be tensile tested. As you can see, we sliced 5 dog bone samples and printed them all at the same time to maintain consistency. The shape is so that we could fixture them in our setup, which, while simplistic, did end up providing good results. We sliced them in Cura and modified the way Cura works to remove all of the walls it would typically print so that we just have those rasterized angle infill layers of 45 degrees and negative 45 degrees with no other elements. Some of the papers we looked at used Cura to generate used Python to generate their G code, but we decided it would be simpler to just modify Cura instead. These are the samples we then tested.
So this first picture shown on the left is the sample of the 3D printed parts, and it is actually shown after its failure. And to the right of that, you'll see this little short video of our testing setup, which I will play now so you can see. Alright, so you will see that we have a bucket which is attached to our 3D printed sample, and we are slowly adding weight during this process to determine the failure weight for this particular part. And this average failure load was looking at around 493.2 plus or minus 5.3 newtons, and we had about 98.4% of predicted value of a 501.4 newton prediction. And below that is just a breakdown of our various trials. You'll see we have 5 separate trials that we ran during this test, and there was an average of 110.88 pound failure, and the standard error is looking at about 1.18, which is pretty great. I would say so myself, and this was just basically the testing process that was behind the scenes of this analysis.
As you saw in the testing process, the model that we developed here did very accurately represent the actual failure load that we saw in the real world. We believe this is because the math is overall well-founded and well-described, and part of that is because it's heavily tied in to continuum mechanics, which is very well-defined and accepted as a theory. So the first connection we see is that we use the rule of mixture, which allows us to create one continuous medium so that we can then analyze it with continuum mechanics as opposed to 2 distinct phases. Most of the math for composite laminate theory is derived from the linearized elasticity general equations from chapter 23.2, which you can see on the right. Although we are taking these C property tensors and rotating them using transformations like we learned in class to see the appropriate coordinates for each layer and then summing them. Finally, the Tsai-Hill failure criterion that we use is a strain compatibility enforcement regime. So it looks at stress energy in each layer and compares it to how much displacement that is going to create and whether that is compatible with the surrounding layers. And if the displacements are incompatible, then there is shear and disconnection between the layers, and the layer is considered to have failed.
One critique we have for the paper is the author's stated intent to capture the dynamic process of extrusion of a filament material inside of the void shape factor. Extrusion of the filament material involves a phase change past the glass transition temperature, involves some amount of stress and relaxation during the extruding process, and a dynamic recrystallization rate that can be a factor of different cooling effects which the printer can produce. This paper doesn't make a convincing case for this assumption, or it doesn't really convince us that you can capture all of these dynamic effects within a single void factor. However, the efficacy of the overall analysis in the paper is not necessarily problematic, but the assertion that the shape factor captures enough information about the dynamic process in order to truly say we've described it is not supported. The critique we have with the paper is that the paper uses classic laminate plate theory, and it heavily depends on classic laminate plate theory for its overall analysis, but it does not specifically limit the scope of its overall analysis to plane stress systems. The plane stress assumption is stated in the paper a single time, but it is not enforced as a limiting factor for the method of analysis for a greater part. It is only referred to in the essence of analyzing one layer. It is then implied, essentially, that the plane stress limitation is used layer by layer, but the overall part may experience some triaxial stress. This raises concerns about the validity of the overall analysis when applied to a complicated part. Final critique with the paper is it's rather antiquated in terms of printing technology. The effects of lattice-based infill are not considered in this analysis. This analysis assumes that each layer is uniaxial fiber directions. No modern printed parts are really made like that today, as it is not very material efficient. You end up using a lot of material in places that you don't need it, and it becomes relatively expensive. Additionally, the effects of perimeter walls in the different directions to the interior infill and overall the rest of the medium are disregarded. These are crucial elements of modern 3D printed parts which rely heavily on walls and infill rather than uniaxial layers, which again raises questions about the validity of this analysis type for any modern 3D printed part.
Here we have our sources for the testing process and for this presentation. If you have any questions, please feel free to contact any of the team members via email. Thank you again for your time. Have a great day.